Hello, everyone. I hope you're doing well. My name is Rami Herrick. I'm an associate professor of mechanical engineering at the University of South Carolina. I will be presenting to you today our work relevant on the thin plies, on the exploration and manufacturing with automated fiber placement. So I will go ahead and start by presenting my co-authors. Andrew Lovejoy and Don Jegley from the Structural Mechanics and Concepts of Branch at NASA Langley, Catherine Jochen from the University of Bremen in Germany. Let me go ahead and get started by saying that this work was conducted within the Isaac group at NASA Langley. You can see here in the pictures the Isaac team that is led by Don Jegley, and you can see several of the folks that operates the automated fiber placement machine at NASA Langley. This is the AFP machine. It is one of the most versatile AFP machines that has multiple heads. You can see in here the head of the AFP machine, and in few slides, I will be showing the system and talking in details about it. This is the integrated structural assembly of advanced composites research team at NASA Langley. So this is the table of contents for our presentation. This is how this presentation is gonna go. First of all, an introduction on the benefits. Why thin plies? What would be interesting to adopt a unconventional material and taking a lower GSM than the standard ones. And the way that we're going to do that is we're going to talk about three sets of experiments. We're going to talk about the exploration when it comes to laying on a flat geometry with 70 GSM, also using a flat geometry, flat panel for 30 GSM, but also we are going to take a look into the complex geometry and 70 GSM and the trials. The presentation is going to conclude with the manufacturing parameters that our exploration was capable of capturing. Obviously, when we talk about process parameters, we're talking in the world of automated fiber placement about temperatures, pressures, speed, tension, and so on. And then I'm going to wrap up my presentation with some concluding remarks. So let's go ahead and get started. It's very important, first of all, to highlight that what we have in here is typically we use standard prepreg material with automated fiber placement. Standard prepreg material is between 140 GSM to 170 GSM. To avoid confusion, especially that I'm going to repeat this a lot, when I mention GSM, this is this ratio of grams per meter square. And actually GSM stands for this. We're talking about the fiber areal weight. So taking a look into this, instead of using the standard prepreg material, we're going to go ahead and propose using a thin-ply material that has lower fiber areal weight, ranging from 15 GSM to 70 GSM. And in this paper, what we are actually trying out is 30 GSM and 70 GSM. Thin plies, first of all, there is an effect where definitely the laminate laying sequence is going to change. It's not going to remain the same. However, there are tons of benefits. Tsai et al. Talked about 10% increase in the ultimate strengths. Lovejoy and Scotty talked about the amount of weight savings that can be induced by using thin plies or by having a hybrid between thin plies and standard plies in comparison always to standard plies. And when we say standard plies, we're talking about plies that have a standard 140 to 170 GSM. Also, it's very, very important that because we increase the number of plies, the onset of delamination damage is going to be delayed according to Kim and Sonny. So let's go ahead and introduce the automated fiber placement with thin-ply. This is the set. This is the automated fiber placement machine at NASA Langley. What you see in here, and I'm highlighting it with the mouse, is a linear track. This linear track is where this KUKA-based robot going to travel to provide maximum reach. And we have the AFP head that is mounted. This is a electro-impact machine. This electro-impact machine is laying up on a tool. This tool, you can see it in here. This is the complex shape. And what you can see is a coupon table in here. And from the other side, we have a rotator for more complex geometry. Basically, what we have in here is an additional degree of freedom that in here, the robot, you have 6 degrees. By adding the rail, that's 7. And if you add the rotator, that becomes 8 degrees of freedom. Isaac is used for AFP research. And automated fiber placement, prepreg toes are laid simultaneously by the AFP head. It's very important to highlight something, that Isaac is one of the most versatile, if not the most versatile, AFP machine out there. We are equipped with 2 stitching heads. We are equipped with a ultrasonic knife, a projector head, and inspection capabilities, non-destructive inspection capabilities. So there is a plethora of options when you are working with Isaac. Now, what we're trying to do is we're trying to find the optimal process parameters. So we're performing the experiment, and we're repeating it until we find a near defect-free layup. And we're trying to correlate between the process parameters. And obviously, as with any design of experiments, we're going to vary the trials and the process values until we find the most optimal one. So this is something very important to highlight prior to kicking off the discussion on the different experiments. This is the flow chart that we use at Isaac to go ahead and run an automated fiber placement project. What you see in here is a first step of design assessment. This design assessment, this is where we can propose refinements, and we actually do DFM studies. Very often, minor tweaks to the design render it more accessible, more manufacturable, of course, if it meets the constraints. Then, once the design and the geometry concept is validated, what we do is 2 parallel steps. One step relevant to computer-aided process planning, and this step was computer-aided process planning. This is where we are generating the numerical comment, and we're doing the property selection, and so on. So at the end of it, what we would have is a functional code. From the other side, what we're doing is a tool for manufacturing. And this tool for manufacturing is to actually 3D print a prototype. We take it to the cell, we verify this, we validate this, and then we actually obtain a functional tool. Once you have the code and the tool, we perform what we call dry runs. So we're laying up without the material, and then we proceed to automated fiber placement. So the cycle goes as you assess your design, then you start with 2 parallel routes to obtain the functional code and a functional tool. You perform your dry runs, and then you proceed with automated fiber placement. So let's go ahead and start talking about the experiments. The first experiment in the exploratory trials was using the 70 GSM material on a flat surface. As you can see in here, the goal is to identify what are the process parameters that are necessary to lay the plies. Obviously, we always want to minimize the defects. You can see how much we have annotated every layup. You can see in here, so several courses were run at a certain speed, other courses at a different speed. You can see we looked into toe wandering, gaps, overlaps. We did some measurements. And what we did is we adjusted those parameters in between different trials, and we kept moving Of course, obviously, process parameters. So we're looking into temperature, into compaction forces, into speed. We did, however, maintain a constant tension. And this is an example of the effect of the feed rate on the ply quality using two different speeds. So this is an example of a ply at -45. So with the 70 GSM, and you can see some of the toe wandering and the angle deviation effects. And this is another up close zoom on a toe fold, on toe wandering, and on boundary issues. And this is a placement in ply 2 that was at a 0 degree. So we kept repeating those trials until we reached a defect-free application. So this was ply 17, part of the exploration. And one of the things that we found out is the application of a flash tape on the side where the AFP machine actually accesses to perform the manufacturing process. This location actually helped us a lot. Look at the difference in on this picture on the flash tape. So in here we had the flash tape, in here we did not have it. So basically where we had the flash tape, we did not have to perform any repairs. We had, obviously, with the process conditions that we've reached and with this minor addition versus severe repair needed on the other side. So this is with respect to the flat 70 GSM. Now, the flat 30 GSM is a completely different ballgame. For starter, the 30 GSM is so thin that it needed two backing tapes in the roller. And therefore, we needed to remove these two backing tapes. And according to the trials, we had a lot of roping due to the tension. So what we ended up doing is this exercise where we actually designed and 3D printed a second take-up spool. And this second take-up spool that we have done, you can see in here, this is the original take-up spool. And this second take-up spool actually takes the second backing tape. So the first one comes and rolls in here, and the second one is in here. And this is to remove the second backing material at a different stage than the initial one, and providing the toe with enough thickness that actually it can travel without roping up to very close to the deposition, and then we remove this second element. So this was very, very important, and a very important thing that we have done through our exploration. And here you can see several examples of the manufacturing trials with the flat 30 GSM. So you can see we've tried different speeds and so on. And you can tell in here the highest quality of layup was reached within 20% of the speed. In this location, we have tried and we have overlapped so many trials at different fibers and different angles. And all of this, the goal was to find out what are the optimal processing parameters that we can have. So in these two different starting points, what we did is a flatted geometry 70 and 30 GSM. Obviously, the 30 GSM needed hardware modification as well. In this example, in this third trials of exploration with thin plies, what we did is, since we found out the optimal functional process parameters for the 30 GSM, we actually tried this out instead of a flat plate on a complex shape. To do so, what we used is the predict shape. The predict is our trial, and you can access this paper from SAMPI of last year for a wind turbine manufacturing. And what we did in here is, once again, we varied the heater output, so temperature, compaction, and feed rate. And the defects were identified between the plies. You can see in here the placement on Isaac, and you can see the predict tool. This is the tool that has complex curvature that we actually study and investigate. These are some elements that were observed, very, very important ones. First of all, we needed to use a smaller roller instead of the wider roller. And this is to minimize the issues of the wider roller picking up toes as well as accessibility issues. But also we've noticed the need for a more frequent cleaning of the AFP head that was recommended because of the resin buildup on the redirect rollers. And you can clearly see here the resin buildup that necessitated this more frequent cleaning of the AFP head. So this is in summary the manufacturing parameters that are the resulting manufacturing parameters that we observed to minimize the defects that require repair. Something very, very important to mention in here is that Isaac operates in a clean room environment. So repeating the experiment under the same condition is a natural thing because temperature and humidity are maintained in the environment. So let's take a look a little bit into the manufacturing parameters. So for the 70 GSM, we use the Torre 3900-2, T800S. For the 30 GSM, it was Hexply IM7 85552-1. And these are the different trials that we had. And in here, you can see these four elements, the listing of the optimal heater output, the optimal compaction forces, the optimal feed rate, and the optimal toe tensions. So, and the units are listed in here. So you can see where for the same material, the complex and the flat, you can see that, for example, the feed rate, instead of it being 200 inches per minute, 400 worked better with the complex. However, the compaction, 100 pounds compaction for this flat panel, whereas for the complex one, we had 50 pounds. So we can see a little bit that these different manufacturing parameters that we were able to observe and to use for the manufacturing and the exploration of the thin-ply parameter. And finally, to conclude the remarks, the use of the 30 GSM and 70 GSM was examined using the automated fiber placement robotic system at Langley. We identified the manufacturing parameters to minimize defects for several ply orientations, and the results indicate that both materials form have potential for application in a relatively defect-free manufacturing, obviously while using the optimal manufacturing conditions. With that, I would like to thank you for listening to my talk. I invite you to read the paper, and if there are any more information, please feel free to communicate with me, email me, harik@cec.sc.edu, and I will be more than happy to respond to your questions. Thank you very, very much.